Okay, in this section, or sorry, this lecture, we're going to cover section 3.5, and that's on implicit differentiation. So let me share my screen. Hopefully you can see what I'm seeing. So the idea is that so far, we define what a derivative is. It can be thought of as the rate of change of some quantity with respect to another quantity. So rate of change of position with respect to time. And so what we have been doing is differentiating functions so far. So far, we've oops, been differentiating functions. But it turns out that you can actually make sense of taking the derivative or differentiating an equation. In fact, we've actually been doing that all along. So given a function, say f from some domain E to some set E, um, let's say actually say it's differentiable. So given a differentiable function f from some set E to nope, I get it backwards. Usually D stands for domain and E is our range or our codomain. So given some differentiable function f, we can, or just given any function actually, we can form the equation y is equal to f of x. And this is how we graph equations. Remember, you given any equation involving variables x and y, so we usually think as x is the independent variable and y is the dependent variable. The idea is that as x changes, y changes. So you can talk about how the rate at which y changes with respect to x. And given any equation, we can in terms of x and y, we can look at all the points x comma y, all the ordered pairs which satisfy the equation, and this will determine a curve in the xy plane. And then remember, we had a criteria that said a curve um, comes from a function if and only if it satisfies the vertical line test. So we saw that if I give you an equation, you can plot it, and then we saw that not every equation corresponds to some function. And the idea is that not you can't always solve for y explicitly in terms of x. You can't write y as some function of x. But if I give you a function, in particular, we're going to talk about differentiable functions, you can form this equation, and of course you can graph it. But you can also differentiate the equation. So we can differentiate the equation. So we like apply this derivative. So we're thinking about this as an operator. So it's like we're applying this operation to both sides of the equation, and we get the derivative. So it's like if we square both sides of an equation, you have this operation of squaring, or if you add both sides to equation, you have this operation of adding both sides, adding. So you're adding both sides to the equation. So we're going to perform this operation, and as I said, it's actually what's called a linear operator, but that's sort of besides the point. We can take both sides of this equation and apply this operator to it. So we get dy dx is equal to, sorry, this is not, shouldn't be there. It's going to be on here on the second line. Then dy dx is equal to f prime. But as I said, not every um, equation comes from or determines a function. So there are some equations that don't correspond to functions. So for example, we have the equation x squared plus y squared equals 1. This this does not define y as a function of x, because if you try to solve for y in terms of x, you're gonna end up with a square root, a plus or minus square root. So there's no unique point. Remember, what does it mean to be a function? It means if I give you an input, there's a unique output. Um, but if I plug in a specific x for you here, there are going to be two y values associated, one for the plus root, one for the minus root. But it still makes sense to differentiate this equation. So this does not define y as a function of x. However, we're going to see it still makes sense to talk about derivatives of equations from two different perspectives. For one, on the one hand, however, y is still changing with respect to x. So if I plug in a specific x and then you solve for y, you're going to get some numbers, or actually in this case, you're going to get two numbers. If you plug in a different x here, you're going to get different y values. So y is in a sense still changing with respect to x, just not in a unique way, really. But we can still talk about the rate of change. So it still makes sense to talk about, we'll put in parentheses, instantaneous rate of change of y with respect to x. And that is to say, i.e., dy dx still makes sense. It might not be a function that's right here, but it still makes sense to talk about y changing with respect to x. So this is going to be the sort of reason why it still makes sense to talk about the derivative of y with respect to x when you have this equation involving x and y. On the other hand, from another perspective, that is the tangent line problem. Let's draw, when we draw this equation, we get a terrible circle like this. Let me actually see, maybe there's a tool. Actually, there's a tool. So we get a circle. I don't know how to, okay, here we go. You get the unit circle. And then we'll not that. Let's see if I can draw x and y axis. So we have x, and then we have y, and we're plotting the equation x squared plus y squared equals 1. Remember, what is the other aspect of derivatives? Well, remember, the derivative gives you the slope of the tangent line. And so I have this curve, and certainly makes sense to take a point on this curve and look at tangent lines, which is precisely what the derivative gives you. It gives you slopes of tangent lines. So I can look down here and I can look at this tangent line. So it still makes sense to talk about derivatives because derivatives give you slopes of tangent lines. It still makes sense to talk about slopes of tangent lines. You're going to see there's going to be a problem here though because we get this vertical tangent line. And we're going to actually figure out how to differentiate this in a moment. But you'll see that at this point right here, this point right here, we have vertical tangents. So however, whatever it means to take the derivative of this equation, it should be the case that we don't have differentiability at these 2 points because we have vertical tangents, and we'll see that that's the case. Those that phenomenon will pop out in the derivative. It will make sense. So the idea is really simple. It's the following. Given given a general equation, say like the circle maybe, and we're going to say not necessarily corresponding to a function. So maybe and what that means geometrically, for example, uh, is that if you plot the curve associated to this equation, it's not going to pass the vertical line test. So for like example, you could take the circle. We can, and this is where we make believe, we can imagine that um, imagine y is a function of x, even though it really isn't. We can sort of treat y as a function of x, and it's just maybe not possible to solve. So y is some function of x, and when we differentiate y, or we differentiate y to some power, we need to use chain rule. So if we differentiate a term, and in the equation say y squared, we need to use the chain rule. Oops. All right, so what does that look like then? What does it um look like to take the derivative of, say, the circle? So we have x squared plus y squared is equal to 1. And so what we're going to do is we're going to apply the derivative operator to both sides of the equation, because the derivative is just an operation like, say, squaring or adding or multiplying or dividing. And if you do an operation to one side of the equation, you have to do it to the other side of the equation. And now we can use the fact that derivative is a linear operator, so I can take the derivative of this sum is the sum of the derivatives. And then now the derivative of constant 0, so that's nice. I gotta pull this down a bit. Let's see. All right, so now for this term, we just differentiate it like we usually do. It's x to some power, so we use the power rule to get 2x. Now here's where things get a little bit different. We're differentiating y with respect to x. Here we're differentiating x with respect to x. So we're differentiating x squared with respect to x. So we just use our usual rules, but for when we come across a term like this, again, if it helps, you can imagine that y is some function of x. So we need to use here the chain rule. Why? Well, it's y chain rule because y y squared, I should say, whoops, is y composed with the squaring function, right? So I need to use chain rule. So our inside quote unquote function is going to be y, and our outside function is going to be the squaring function, the 2. So what we're going to get is we're going to get 2 times y. So the power, so if I take the derivative of the outside function, it's like you can think of it as x squared. I have to bring the 2 down, but now I have to evaluate that the outside function at the inside function, so that's going to be y, and then I have to multiply by the derivative of the inside function, which is y prime. And this is exactly what we want to find. This is what we are trying to find. So now we can solve for this. So we get y prime is equal to, so I'm going to subtract, first of all, I can divide the 2's out, and then I'm subtract x, and then I'm going to divide by this y right here. So I get y prime, that is the rate at which y is changing with respect to x is equal to negative x over y. So this is clearly not really a function either. But that's okay. So somehow the rate at which y changes depends on x and y, really. But notice this is exactly notice where we're not differentiable. So we're not differentiable. when y is equal to 0, right? So that corresponds to what points? -1, 0, and 1, 0, right? And that those are exactly where we have these horizontal tangent lines, right? This point right here is -1, 0, and this point right here is 1, 0. So this process of differentiating equation gives us the right result, and it syncs up with everything. It syncs up with our geometric intuition about what a tangent line is. It's a point to a curve that touches the curve at one spot and it kind of follows in the same direction. And if you draw the tangent lines here, you get vertical tangent lines. And that should mean, which is like infinite slope. So we shouldn't have we should not have let's say the derivative equal to or shouldn't be differentiable at those points. And that's exactly what you get. What happens, like say x is really close to 1 but not quite 1, right? So it's like 0.99999. And now you're going to let y approach 0. What happens? Well, this fraction blows up to either plus or minus infinity, depending on whether y approaches well, yeah, I'll just leave it at that. It's gonna blow up to, well, actually no, I think it'll just blow up to, that's actually a good point. So blow up to plus or minus infinity. The point is it blows up to an infinity, right? As y approaches 0, because I don't think it could approach 0 yeah, no, it can approach 0 from the left or the right. So if it approaches 0, if y approaches 0 from the right, then this will be positive infinity. If y approaches 0 from the left, it'll be no, it'll be backwards. I'm sorry. Hopefully the point isn't lost though. What I'm trying to say. If y approaches from 0 from the right, it's going to be negative infinity, and then from the left, it's going to be positive infinity. But in any case, the derivative blows up at this point, near this point, -1, 0, and 1, 0. And so all of this is like syncing up. It's like there's like everything is kind of consistent. There's a consistency. And so this is should suggest that this is the right thing to do. And in fact, it is the right thing to do. All right. So now, so this gives us, so what this, one way of thinking about this is the rate at which y changes with respect to x. Alternatively, y prime, which is equal to x over negative x over y, gives us the slope of the tangent line to the curve x squared plus y squared equals 1 at the point xy. So you have this point xy on the circle, on this curve, the circle, and this expression right here gives you the slope of the tangent line at that point. All right, so that was kind of like the motivating example. So now we have this general procedure of calculating or computing derivatives of equations to find out in terms of x and y, and to find out how y is changing with respect to x, or finding tangent slopes of tangent lines. So let's work through another example in the book. Let's see. All right, so this is going to be example 2. So this is all on implicit differentiating. The idea is that y isn't explicitly a function of x. It doesn't, you can't really describe explicitly how y changes with respect to x, because maybe you can't solve for y in terms of x, like say with the example of the circle, but there is like this implicit relation between x and y, and you can determine how y changes with respect to x. So this is implicit differentiation. So what we want to do is find the derivative. Oh no, sorry. So there's just like a couple parts. I'm going to combine two parts of this problem. Um, so this is actually an interesting problem. So this is A and B. I'm going to combine parts A and B. So we want to find the equation of the tangent line to the curve. This is called the folium of Descartes, whatever that really means. X cubed plus y cubed is equal to 6xy. Descartes was a very important mathematician and philosopher. Um, so we want to find the tangent to this curve at the point 3 comma 3. So first of all, we need the derivative. So we're going to differentiate both sides of this equation. And then we're going to solve for y prime. All right, so now we could just use, oh, I need some more room. All right, so I can use linearity of the derivative. In fact, it's a linear operator to just differentiate each term individually. So when I differentiate this one, I get 3x squared. This is the power rule. But now this, I got to use chain rule together with the power rule because it's y composed with x cubed, right? So by the chain rule, I take the derivative of the outside function, which is our x cubed. So I get 3. So I bring the power down and then I reduce the power by 1 to get 2. So I have x squared. But then I have to compose that with the inside function. So I get y squared and then times the derivative of the inside function, y prime. Now on the right hand side, I have a function of x, which is just x, times this like other function, quote unquote, function of x, which is y. So I need to use the product rule here. Because y is not a constant. Y is changing with respect to x. So if you multiply two things that are changing with respect to x, you have to use the product rule. So I'm going to just factor out this 6 because that's a constant. I can take that out. I can't take the y out of this different derivative. It's not a constant. And the product rule says I take the derivative of the first function, which is just going to be 1, times the second function, plus the first function times the derivative of the second function, which will be y prime. All right, so I'm going to divide both sides by 3. And so what I have is a y prime here and y prime here. So I need to solve for y prime. So I divide by 3, and I get x squared plus y squared times y prime. And then I'll get a 2 here, and I'll distribute that through. So I get 2y plus 2x prime, 2x times y prime. And so I'm going to put these two together. So I'll get y squared times y prime minus 2xy prime is equal to 2y minus x squared. Factor out this y prime, you get y squared minus 2x is equal to 2y minus x squared. Oops. And then now I can finally solve for y prime. So y prime is going to be equal to 2y minus x squared over y squared minus 2x. And so if I evaluate y prime at the point of interest, which is 3, comma 3, I can get the slope of the tangent line at this point. So it's going to be 2 times 3 minus 3 squared over 3 squared minus 2 times 3, which is, I guess this is like, actually, this is just, the top is just the negative of the bottom, isn't it? That's weird. Wait, how is it? No, it's not. Not quite. But this top is the bottom of the negative, is the negative of the bottom, but it's not in general that's not in general true, I don't think. Let's see. Anyways, so if you simplify the top, you get 6 minus 9 over 9 minus 6, which is -3/3, which is equal to -1. So we have the slope. So this implies that the line, so the tangent line, is given by y minus 3 is equal to -1 times x minus 3, and then you can solve for it if you want. So you get negative x, and then negative, so plus 3 plus 6, another 3 is equal to 6. So it's negative, y is equal to negative x plus 6. All right, so the next part of this problem, so this was kind of combining A and B, is we want to find out, oops. All right, let's see. Put them in now. So part C is we want to, so the question is at what point in the first quadrant um is the horizontal line tangent, or sorry, is the tangent line horizontal? So um so the tangent line horizontal if and only if slope is equal to 0. And the derivative gives you the slope. So that's if and only if y prime is equal to 0. So we just need to set our derivative equal to 0. And what we found, so we have to set y prime equal to 0. And what we found, recall, is that y prime is equal to 2y minus x squared over y squared minus 2x. So that's the same thing. So if we set it equal to y prime equal to 0, it's the same thing as 2y minus x squared over y squared minus 2x is equal to 0. And that's the case if and only if the numerator is 0. So we get 2y minus x squared is equal to 0. And that implies that, well, I guess y is equal to um, x squared over 2. All right, so this is, so you can see it's not just one single point where you have horizontal tangents. There's a lot of points on the curve, or could be a lot of points on the curve where you have horizontal tangents. So we need to plug this back into original equation. Original equation. So when we do that, so remember the original equation was that we have 3x squared. Oh, sorry, no. We have x cubed plus y cubed is equal to 6xy. So now we want to replace y with this right here. So when we do that, we get x cubed plus x squared over 2 cubed is equal to 6 times x squared over 2. And let's see, what do we get? We get x cubed plus x to the 6 over 8 is equal to, when you simplify this, you get 3x. This is a square, I think, yeah. So that'd be 3x to the third. So then you can, I guess, what's the easiest way to do this? I feel like I did something wrong, actually. Well, I guess what I'll do is no, I think this is right. I'm going to multiply sides by 8. So I get 8x cubed plus x to the 6 is equal to, I guess, what is that, 24x cubed? If I didn't screw that up, which I often do. So then this implies that x is equal to, what's the easiest way? Just, well, I guess I could subtract 24 4 from both sides. Well, actually, okay, actually, I'll just leave it x cubed. Subtract 8 from this, you get 16. Wait, is you get 16? Yes, you get 16 x cubed. And now, so here's the important observation. In the first quadrant, which is the quadrant that we're interested in, x is not 0, right? Unless you're on the, yeah, if you're on the x-axis, but we don't consider that part of the first quadrant. So that means I can divide by x, because x we're assuming is non-zero, or at least we're assuming we have a point in the first quadrant, so that implies x is non-zero. So you can divide by the x cubed, you get x to the third is equal to 8, and then you get, when you take a cube root, you get x is equal to, oh no, not 8. You get x to the 16. And then when you take a cube root, you get x is equal to 16 cube root. And then I guess two, all right, I guess you can write, okay, I'm just kind of following the book a little bit. I don't know why they do this, but you can write 16 as 2 to the 4th, so it's gonna be 2 to the 4 thirds, I guess. Okay. I don't really know why you care to do that. So this is x. So we actually found a single x, and then remember y is equal to 1/2 x squared. So remember, all the points of where you have a horizontal tangent are of this form. So if you know what x is, you can figure out what y is. So y is going to be equal to 1/2. I guess that's why you want to put it as 2 to some power, because you're going to divide by 2. Okay, that makes sense now. So it's going to be 1/2 of 4, 2 to the 4 thirds. So that means, oh, squared. And then that means you get 1/2, 2 to the 8/3. And then when you divide by 2, so you subtract 1 from the 8/3, and then you get, so it'd be 8 thirds minus 3/3 would be 2 to the 5 thirds, if I got that right. So that means we have a horizontal tangent at the point 2 to the 4 thirds, comma 2 to the 5 thirds. And the book is telling me that that's approximately the point 2.5198, comma 3.1748. Okay, so kind of keep that in your head. I'm gonna pull up the book now because they kind of give a representation of what's going on. So first of all, so this is part C, and they did all this algebra and they found that the horizontal tangent is at here, which is what we saw, and it's approximately this point. And I guess what you can see is, like, here's part of the curve, and then this point is like, it's a little bit above 3. So this point right here would be 3. So it's just a little bit above 3, and that's exactly what the y coordinate is. It's 3.17. So it's a little bit above 3. And then if you trace down the x-axis, so this would be 2 and 3. And look at that, yeah. Our x coordinate is 2.5, so roughly between 2 and 3. So it's looks like that's pretty damn close to being horizontal tangent right there. Draw that. So that's what we did in part C, and then just to back up a little bit, part A, which I combined with B, we solved for y. Let's say we differentiated both sides of this. Oops. We differentiated both sides of this equation right here with respect to x, and as I said, we regarded y as a function of x. It's not like It's not like the most accurate thing to do. It's not really a function of x always. Well, actually, in this case, it's not. Look, it doesn't even satisfy the vertical line test. Like, got intersection at three different points. So this is definitely not a function of y. Y is not a function of x, but you can still like kind of treat it as a function of x in a sense. So you have to use chain rule on the term y cubed and then the product rule on the 6xy, which is exactly what we did. And we found that the derivative was equal to that. And when you plug in x and y are equal to 3, you got -1, which is exactly what we did. And so at this point, 3, 3, you have the tangent line that looks like that. It's like a slope. It has a slope of 1, -1. All right, so let's look to see how many other examples do we have. All right, so we got this. We actually just have two more examples, so let's work through those because this is kind of a tricky concept. All right. All right, so this is going to be example 3. So what we have, so we want to find y prime if y is equal to sine, sorry, no, that is not what y is equal to. We have that the equation is sine of x plus y is equal to y squared cosine x. All right, so now what we want to do is, oops, we want to take the derivative, apply the derivative operator to both sides. So we're taking the derivative of sine of x plus y, and it's taking the derivative. On the other side, we have the derivative of y squared cosine x. So we have sine composed with x plus y, and then over on the right-hand side, we have a product of two functions of x. So the derivative of the left-hand side, so our outside function is cosine, sine, sorry. So the chain rule, so we have to use the chain rule. So chain rule on this, and then we have to do product rule because of this, we have product rule. But then on this term, when we use, after we use the product rule, we have chain rule. All right, so on the left-hand side, we're going to take the derivative of the outside function, which is cosine, evaluated at the derivative of the inside function, times the derivative of the inside function. So we're taking the derivative of x plus y. So it'll be 1 plus 1 y prime. And on the right-hand side, we're going to do product rule. So what does the product rule say? Well, it says take the derivative of the first function. So I'll just write it out like that for now. And then times the second function plus the first function times the derivative of the second function, which is cosine of x. Oops. All right, so now the let's just copy down the left-hand side times 1 plus. Actually, what we need to do is distribute. Let's distribute and then kind of move terms around because we're going to need to solve for y prime. So what we'll have when you FOIL this right here, you y prime cosine of x plus y, and then plus cosine of x plus y, and then on the right-hand side, you're gonna now we apply the chain rule to this piece. So it's gonna be, we actually did this already. It's gonna be 2 times y prime cosine of x, and then plus well actually now we need to take this derivative cosine. Remember that's gonna be negative sine, so it's gonna be negative y squared sine of x. And so we have a y prime here and then a y prime here. So let's put those terms together. So we're gonna get y prime cosine of x plus y minus 2y times y prime cosine of x is equal to negative cosine of x plus y minus y squared times x, sine of x. And now I factor out the y prime. So y prime times the cosine of x plus y minus 2 times cosine x is equal to all of this. Just copy it down. And now I can divide to solve for y prime. So y prime will be equal to negative cosine of x plus y minus y squared sine of x all divided by cosine of x plus y minus 2y times cosine of x. So I have a negative here, a negative here. I can like factor out the negative in the numerator and multiply it into the denominator. So these negatives right here will go away and these two terms will switch. So it will be cosine of x plus y squared sine x over 2y cosine x minus cosine x plus y. All right, so actually I think that's all we need for now. Let's see. Do I want to actually what is this problem? This one looks kind of I actually don't think I did anything like this, so there's an example for it's about doing a second derivative. So I don't think there's a homework on it. Maybe there is. I'm not going to go over it because it's more or less the same thing, but I definitely encourage you to read through example 4. If there is a problem like that on the homework, or if it's something you want or need to know. So that's all we'll have for this lecture.